All right. Bismillahirrahmanirrahim. In first part, we have covered the engine operating characteristics. Now, we continue the same topic now with respect to the in operating characteristic with respect to torque. Now, torque is a good indicator of an engine's ability to do work. It is defined as the force acting at a moment distance and has a unit of Newton meter or foot pound feet. So torque is a force acting at a moment arm. Torque tau is related to work by this formula. 2 pi tau is equal to brake work of one revolution. And we know that brake work of one revolution is equal to brake mean effective pressure into the displacement volume divided by the number of revolutions per cycle. So this is the general equation for torque. Now, for two-stroke engine, with one cycle for each revolution, the formula becomes the 2 pi tau is equal to WB is equal to brake mean effective pressure into displacement volume. Now it's a two-stroke, so we have this tau, 2 pi tau, so tau remains there. Brake mean effective pressure into displacement volume divided by 2 pi. Now, if we have a four-stroke engine with one cycle for two revolutions, so it has to cover 360 plus 360, 720 degree of revolutions. So the formula becomes for torque is tau is equal to brake mean effective pressure into displacement volume divided by 4 pi. So brake mean effective pressure and brake work WB are used because torque is measured of the output crankshaft. So it is not something which is indicated work or indicated mean effective pressure. It deals with the brake mean effective pressure and brake work because it is measured at the output end, and that output end is your crankshaft. Now, torque. Many modern automobile engines have maximum torque in the 200 to 300 Newton meter range at engine speed usually around 4,000 to 6,000 RPM. So we have a speed of 4,000 to 6,000 RPM and the torque ranges from 200 to 300 Newton meter. The point of maximum torque is called maximum brake torque speed. Maximum brake torque speed. A major goal in the design of a modern automobile engine is to flatten the torque versus speed curve and to have high torque at both high and low speed. This is the major goal in designing the modern automobile engine. You have to flatten this torque versus speed curve, and you have to have high torque at both high and low speed. CI engines, the compression ignition engines, generally have a greater torque than SI engine. It is usually found like this. Larger engines often have very high torque values with maximum brake torque speed at relative low speed. Now, torque and power as a function of engine speed. First, I read this. Brake power and torque of typical automobile reciprocating engine as a function of engine speed. Speed at which the peak torque occur is called maximum brake torque or maximum best torque. Indicated power increases with the speed while brake power increases to a maximum and then decreases. This is because friction power increases with engine speed to a high power and becomes dominant at higher speed. More the speed, more the friction losses are. So this is the case. Shows power and torque curves for specific engine. Now we have these two engines, one with a displacement volume of 3.2 liters and other with a displacement of 2.5 liters. Now on x-axis, we have the engine speed ranging from 2000 to 8,000 RPM. And on the left side, we have torque, Newton meter, 10 to 300 is the range. And we have a power, watt per watt or kilowatt, from 100 to 200. Now, if we let's see with an engine with a displacement of 3.2 liter. More torque at lower RPM is more the RPM, the torque is decreasing. Similar is the case in the power. More the RPM, increasing to a certain limit and then decreasing. Same goes for this. Higher the power RPM is, more the torque, more higher the RPM, lesser the torque, more the power is. Now, power. Another operating characteristics of an engine. Power is defined as the rate of work of the engine. So it is the rate of the work of the engine. If n is small n is the number of revolutions per cycle and capital N is the engine speed, W is the work per cycle, AP is the piston face area of all the pistons, UP bar is average piston speed. So power of an engine we can define as W dot is equal to W n over n, where W is the work divided multiplied by engine speed divided by number of revolutions per cycle. So power is equal to 2 pi n torque in terms of power relation with the torque. Power is equal to 1 by 2n mean effective pressure AP piston face area of all the piston into average piston speed. So when we have a four-stroke, then the equation becomes mean effective pressure, AP the piston face area, UP bar the average piston speed divided by 4. If we have a two-stroke engine, then the power is defined as the mean effective pressure into piston face area of all the piston, average piston speed divided by 2. Depending on the definition of a work or mean effective pressure relationship for a brake power, net indicated power, gross indicated power, pumping power, and even friction power can be defined also as. So the brake power is equal to mechanical efficiency into indicated power. Brake power is equal to mechanical efficiency into indicated power. Indicated power net is equal to indicated power gross minus indicated power pump. So indicated brake power is equal to indicated power minus friction power. So remember these conversions. 1 horsepower is equal to 0.7457 kilowatts, and these 2545 British thermal unit per hour, or is equal to 550 foot force per second, or 1 kilowatt is equal to 1.341 horsepower. This data is important when we have to do numerical for the conversion. We use this data. Okay. Power can be generated by increasing the displacement, means the volume, mean effective pressure, and or speed. So we can, if we want to increase the power of an engine, we can fiddle with these three parameters: displacement, the volume, the mean effective pressure, and or speed. Increasing displacement increases engine mass and takes up space. If we are increasing this factor, displacement, it means we are increasing the mass of the engine, and if we are increasing the mass, then it will cover more space, both of which are contrary to automobile design trend nowadays. For these reasons, most modern engines are smaller but run at higher speed and are often turbocharged or supercharged to increase the mean effective pressure. So we are using the smaller space with small size of engine equipped with turbocharger or supercharger, which in turn increase the mean effective pressure and the speed to increase the power of an engine. Now, some other parameters or operating characteristics of an engine: specific power, P, is equal to the brake power divided by the AP piston face or area of all the piston. Output per displacement. Output per displacement is your brake power divided by the displacement volume. Okay. Specific volumes is equal to your displacement volume divided by your brake power. So it's inverse. Specific weight. Specific weight is the engine weight divided by the brake power. So these are the few important formulas. Modern automobile engines usually have brake power output per displacement in the range of 40 to 80 kilowatts per liter. In latest engines, today's engines, so this is the range 40 to 80 kilowatts per liter. The Honda 8 volts per cylinder V4 motorcycle engine generates about 130 kilowatts per liter, an extreme example of high performance racing engine. One main reason for continued development to return to two-stroke cycle automobile engine is that they have up to 40% greater power output per unit weight. So this trend is like this. Now, how to measure this torque and power? Need to have some device, and that device is known as dynamometer. Dynamometers are used to measure torque and power over the engine operating ranges of speed and load. They do this by using various methods to absorb the energy output of the engine, all of which eventually ends up as heat. Basically, we have a test bench. On test bench, we have a placed engine on the engine output end, the crankshaft where the power flows. The device, the dynamometer is coupled in which we apply some load and speed is applied to the engine and load is applied to the dynamometer, and at different ranges we check the torque and the power. So some dynamometer absorbs energy in a mechanical friction brake, pony brakes. These are the simplest dynamometer but are not as flexible and accurate as others at high energy level. Three general types of dynamometers are fluid or hydraulic dynamometers, eddy current dynamometers, or electric dynamometers. Now, another example. Remember example one. I, this was the statement. John's automobile has 3-liter SI V6 engine that operates on a 4-stroke cycle at 3600 RPM. The compression ratio is 9.5. The length of the connecting rod is 16.6 centimeter and the engine is square. Bore is equal to stroke. At this speed, the combustion ends at 20 degree after TDC. So this was the statement of example 2-1. Now coming back to example 2-2, the same data is that is connected to a dynamometer which gives a brake output torque reading of 205 Newton meter. We have a range of 200 to 300 Newton meter. So it's in that range at 3600 RPM. So RPM is a little bit less. At this speed, air enters the cylinder at 85 kilopascals and 60 degrees Celsius. And the mechanical efficiency of an engine is 85%. Now calculate all these 10 parameters. Brake power, indicated power, brake mean effective pressure, indicated mean effective pressure, friction mean effective pressure, power loss to friction, brake work per unit mass of a gas in a cylinder, brake specific power, brake output per displacement, engine specific volume. Let's find out one by one. Now, using this equation, we know that the brake power is equal to 2 pi n into tau. So we know 2 pi radians per revolutions. We know the RPM is 3600 divided by 60, so comes out the revolutions per second. Torque, the dynamometer is giving us 205 Newton meter. So we can find out the brake power, that is 77,300 Newton meter second. So converting into kilowatts and horsepower, it is like this. Now we have found out the brake power. Now we found the indicated power. Indicated power is equal to brake power divided by the mechanical efficiency. Data is given, we have found out the brake power. So brake power divided by the mechanical efficiency, we get the indicated power. Okay, that is 90.9 kilowatt and the brake power was 77.3 kilowatt. As we know, the indicated value is always greater than brake value. Okay, now we can find out directly from here the friction power, or we can have different formulas in later slide. Now, the brake mean effective pressure, the third thing, is equal to, with same equation, we can find 2 pi tau divided by the displacement volume. 4 pi in radians per cycle. Newton 205 is the torque. Okay. Then the displacement. It's a 3 liter engine, so 0.003 meter cubes per cycle, which comes out to be 859,000 Newton per meter square, so 859 kilopascals or 125 psi. Now, equation. Indicated mean effective pressure is equal to brake mean effective pressure divided by the mechanical efficiency. We have found out the brake mean effective pressure, that was 859 kilopascal, and we know the mechanical efficiency. So we can found out the indicated mean effective pressure, that comes out will be 1010 kilopascal or 146 psi. Now, friction mean effective pressure, we can find out from indicated mean effective pressure minus brake mean effective pressure. Similarly, we can find out this thing. Now, again, using the friction power, we can find out with this formula or with this formula. So let's see. AP is the piston face area of cylinder, pi by 4 b square. This is for one cylinder. Okay. Now, using the equation 2-44, 1 by 2 n friction mean effective pressure, piston face area into average piston speed. Then this piston face area, which we have found for one cylinder, so it is V6. So we have 6 cylinders now. Now it comes out to be 13.6 kilowatt. Another way of finding this, we have already found out the indicated work and indicated power and brake power. So from there, we can find out the friction power, and that comes to be the same as we have found out from this formula. Now, for brake work is found for one cylinder for one cycle. Using this, brake work is equal to brake mean effective pressure into displacement volume. We have found out these. Okay, so we found out the brake work. If it can be assumed the gas entering the cylinder at BDC is air. So we use the standard characteristics of the air. We use the general gas equation. Mass of air is equal to pressure into volume at BDC divided by the universal gas constant into the standard temperature. So we can write this equation. Atmospheric pressure, or the pressure given to us, is PT plus VC, volume at BDC, universal gas constant, and the temperature. So pressure, it's given to us as 85 kilopascal. We know the clearance volume, we know the displacement volume, and putting in the equation, the universal gas constant R is the value of 0.287 kilojoules per kilogram dash Kelvin. And we have the temperature 60 degrees Celsius. So converting into Kelvin, it comes to be 333 Kelvin. So mass of air which is entering the cylinder when the piston is at BTC is 0.00050 kilogram. So brake specific work per unit mass. So brake specific work per unit mass. We divided this brake work divided by per unit mass. So we have this value 860 kilojoules per kilogram. brake specific per work per unit mass. Now putting the value brake specific power. Finding the brake specific power, we have a brake power divided by AP, area of the piston face of all the cylinders. We have sent the value of brake power is 77.3 kilowatt divided by pi by 4.0086. That is the bore of the area of the piston, and into 6. 6 is the number of cylinders, so the all cylinders. So the brake specific power comes out to be 2220 kilowatts per meter square. That is 0.2220 kilowatt per centimeter square, and that is 1.92 horsepower per inch square. Now, gives brake output per displacement. We know the brake power divided by the displacement. This displacement of the complete 6 cylinders, okay? So complete total volume, 3 liters. So brake output per displacement is your 25.8 kilowatts per liter or 35 horsepower per liter. Now brake specific engine volume, total volume divided by your brake power, or 1 over brake output per displacement. So this comes out to be 0.0388 liters per kilowatt. So in this way, we can find different operating characteristics of an engine. Now, the next operating characteristics of an engine is air fuel ratio, or fuel air ratio. Let's see. Combustion requires proper relative amount of air, oxygen, and fuel. If we have a proper amount of air ratio of fuel, then we can have this combustion process. If the air is more, fuel is less, the combustion will be lean. If the air is more, fuel is less, combustion will be lean. If air is less and fuel is more, your mixture will be rich and the combustion will not be the proper. So we have to have a specific ratio, specific quantity, specific amount of air fuel. Air fuel ratio and fuel air ratio are parameters used to describe mixture ratio given by air fuel ratio is mass of air divided by mass of fuel, or mass of mass flow rate of air divided by mass flow rate of fuel. Whereas fuel air ratio is mass of fuel divided by mass of air, or mass flow rate of fuel divided by mass flow rate of air, or FA is equal to 1 over AF. Okay. For gasoline type hydrocarbon air fuel, when you have a compression ratio of 15:1, with the combustions to occur between 6 to 9 is the range. Air fuel is ratio is less than 6, we have a too rich. If air fuel ratio is greater than 19, then we have too lean to sustain combustion. Gasoline fuel engine air fuel ranges from 12 to 18. So this is the range. Okay. In CA engine, having an air fuel input in the range of 18 to 70, because they are also known as compression ignition. So their air fuel ratio range is more. Now, equivalence ratio phi is defined as the actual ratio of the fuel air to the ideal or stoichiometric fuel air given by equivalence ratio phi fuel air actual divided by fuel air stoichiometric, or is equal to air fuel stoichiometric divided by air fuel actual. So this is the equivalence ratio. Now, air fuel ratio and fuel air ratio, specific fuel consumption is defined as mass flow rate of fuel into the engine divided by the engine power. Specific fuel consumption of any engine is related with mass flow rate of the rate of fuel flow into the engine to the engine power. Brake specific fuel consumption is the rate of fuel flow into the engine divided by engine power. Now indicated ISFC, mass flow rate divided by indicated power. So mechanical efficiency is divided is brake power, engine brake power divided by engine indicated power is equal to rate of fuel flow into the engine divided by indicated power divided by rate of fuel flow into the engine divided by indicated divided by brake power. So we can write mechanical efficiency of an engine with respect to fuel indicated specific fuel consumption divided by brake specific fuel consumption. Now, brake specific fuel consumption as a function of engine speed. We have two engines with the compression ratio of 10 and compression ratio of 8. Now, brake specific fuel consumption as a function of engine speed. Fuel consumption decreases as engine speed increases due to shorter time for heat losses during the each cycle. Fuel consumption decreases as engine speed increases due to shorter time for heat losses during each cycle. At higher engine speed, fuel consumption again increases because of higher friction losses as compression ratio is increased. Fuel consumption decreased due to greater thermal efficiency. Now let's see this graph. We have two engines with compression ratio of 10 and 8. On x-axis, we have engine RPM ranging from 0 to 6,000. And on y-axis, we have brake specific fuel consumption, grams kilowatt dash R. So ranging from 360 to 480. So engine with having a more compression ratio is this one. As the speed increases, the brake specific fuel consumption decreases at certain point. When the speed increases, it also increases. With less compression ratio, we have this graph. Now, brake specific fuel consumption as a function of equivalence phi. Okay. Now, brake specific fuel consumption as a function of fuel equivalence ratio phi. Consumption is minimum at slightly lean condition. Consumption is minimum at slightly lean condition, increasing with both richer and linear mixture. Now, this phi is 1 here, means air fuel ratio to the actual to the stoichiometric. 1 is this spot, but here it is minimum when the fuel ratio is towards your lean condition. In lean condition, we have more amount of air, less amount of fuel. In which portion we have less amount of air, more amount of fuel. So brakes, both two engines with a compression ratio of 10 and 8. So the brake specific fuel consumption with respect to the equivalence phi ratio will be like this. Now, brake specific fuel consumption as a function of engine displacement with respect to the volume. On brake specific fuel consumption as a function of engine displacement, generally average fuel consumption is less with large engine. One reason for this is less heat losses due to higher volume to surface area ratio of the combustion chamber is in a large engine. Also, larger engine operates at lower speed, which reduces friction. So we have a displacement volume here on x-axis and brake specific fuel consumption on your y-axis. At when the displacement is small, you have a higher brake specific fuel consumption. As the volume increases, the brake specific fuel consumption decreases. Now, another important operating characteristics is the engine efficiencies. The time available for the combustion process of an engine cycle is very brief, at, and not all fuel molecules may find an oxygen molecule with which to combine, or the local temperature may not favor a reaction. So the explanation of this point is combustion is of specific time period, and that is very, very small, in which all the fuel molecules may not find the oxygen molecules to react with. So, and sometimes the local temperature is not enough to have that combustion properly. Consequently, a small fraction of fuel does not react and exist with the exhaust flow. So the unburned fuel, which is there in the combustion chamber, will move out with the exhaust flow. A combustion efficiency is defined to account for the fraction of fuel which burns. Okay, so we are not taking into account the fuel which is exhausted in the exhaust flow, unburned fuel. We are only talking about the combustion efficiency, account for fraction of fuel which burns. So combustion efficiency typically has a value in the range of 0.95 to 0.98 when an engine is operating properly. When you have a standard or ideal condition, the combustion efficiency ranges from 0.95 to 0.98. For now, engine efficiency for one engine cycle in one cylinder, the heated value, the Q in, the heat in, which is going in, is equal to the mass of a fuel for one cycle into the heating value of that fuel into the combustion efficiency. Okay, the heat generated or heat in is equal to the mass of the fuel for one cycle to the heating value of that fuel which we are using and the combustion efficiency. For steady state, Q dot, the rate of heat in, is equal to the mass flow rate of fuel, the heating value of the fuel, and the combustion efficiency. So from this, we get the thermal efficiency. The thermal efficiency of an engine is the work of one cycle divided by the heat in, heat added, heat generated, or in terms of power, thermal efficiency is in terms of power is power divided by mass, the rate of heat in. Okay, so we can write this equation: power divided by mass flow rate of fuel, heating value of the fuel into thermal efficiency. So we can write all this equation in terms of efficiencies. Thermal efficiency is equal to fuel efficiency divided by combustion efficiency. Now, engine's mechanical efficiency. Mechanical efficiency is the thermal efficiency brake divided by thermal efficiency indicated. The fuel conversion efficiency is equal to the work divided by the mass of fuel flowing, heating value, or in terms of power of an engine divided by mass flow rate, then the heating value. Fuel efficiency, conversion efficiency can also be written as 1 over specific fuel consumption, Q heating value. The thermal efficiency of a single cycle of one cylinder, sometimes called as enthalpy efficiency. The thermal efficiency is the work divided by mass flow of fuel, heating value of the fuel, and the combustion efficiency. Now, another efficiency, the volumetric efficiency. Maximum power can be obtained from an engine by getting the maximum amount of air into the cylinder during each cycle. So, another way of obtaining a maximum power, we induce the maximum amount of air inside the cylinder or inside the combustion chamber. So it means more air means more fuel can be burned and more energy can be converted to output power. Ideally, a mass of air equals to the density of atmospheric air times the displacement volume of the cylinder should be ingested for each cycle. So, ideally, a mass of air equals to the density of the atmospheric air times the displacement volume of the cylinder should be ingested for each cycle. However, because of the short cycle time available and the flow restriction less than this ideal amount of air enters the cylinder. So this is the restriction or this is the design constraint that, however, because of the short cycle time available and the flow restrictions less than the ideal amount of air enters the cylinder. So volumetric efficiency is defined as mass of air divided by density of air into displacement. Or we can also write number of revolutions per cycle, mass flow rate of the air divided by density of the air, displacement volume, and the engine speed. So we can have a volumetric efficiency with these two formulas. Now, air density can be calculated if we know the standard atmospheric conditions that P naught, the pressure, standard atmospheric pressure is 101 kilopascal, means 14.7 psi, and T naught standard we take as 25 degree Celsius or 298 degree Kelvin. So from the formula, density is equal of air is equal to pressure divided by R, which is universal gas constant. T naught is the temperature at atmospheric conditions. Pressure of the surrounding air, temperature of the surrounding air, R is the gas constant for air. We know the value 0.287 kilojoules per kilogram gas Kelvin. So we can calculate the at standard condition, the density of air rho A is 1.181 kilograms per meter cube. We will be using this value in solving the problems. Now, the last characteristics, operating characteristics of an engine is emissions. Main engine exhaust emissions are oxides of nitrogen, which commonly known as NOx, carbon monoxide, CO, and hydrocarbons and solid particles. So the exhaust of emission of any IC engine, internal combustion, is a mixture of NOx, carbon monoxide, hydrocarbon, and solid particles parts. Method of method of measuring the amount of these pollutants are specific emission SE and the emission index EI. So these are the two methods with which we can measure the exhaust emission. One is specific emission and one is the emission index. Specific emissions typically has a unit of grams per kilowatt or while the emission index has a unit of emission flow per fuel flow. So these are the few formulas with the help of which we can find out the specific fuel emission and emission index. When we have specific emission NOx, then we have to find mass flow rate of emissions of NOx divided by the brake power. If we want to find out the carbon monoxide, then we have to use the mass flow rate of the carbon monoxide. If we want to find out hydrocarbons specific emissions, then we have to use the hydrocarbon mass flow rate. And if we want to find parts basically suit the mass flow rate of the parts divided by the brake power. Now, in terms of emission index, in terms of NOx, we have to use the mass flow rate of NOx divided by the mass flow rate of the fuel. Now, in terms of carbon monoxide, the mass flow rate divided by the mass flow rate of the fuel, hydrocarbons, and parts. So this comes to the chapter 2, that is operating characteristics. Now, usually I give this assignment or homework to my students. Solve problem 2-1 to 2-13 In these problems, you will apply all the formulas which we have studied in this chapter. So we will come to know how these operating characteristics are there of that engine we can find. Now, last is the consult book. So this comes to our chapter 2. So kindly like my videos and subscribe my channel. Thank you very much for watching.